The moon has been Earth's constant companion for 4.5 billion years. Now it's finally back in the focus of science, almost 50 years after man last set foot on the moon.
There's more people, the percentage of the total people on this Earth that were not alive when we had the last lunar landing. It's been that long, right? And we haven't done the next thing. And so some people say, been there, done that. But what we haven't done is we've just touched the ground, planted a flag and left, right? We haven't really lived. We haven't explored, truly.
If you want to commit the money to it like we did in Apollo, you could do it in probably 10 years. Easy. We did it in 8 years and 2 months.
Now scientists are concentrating on ways to grow food, produce energy, and make tools there. All over the world, researchers are working on a return to the moon and the chance to be able to stay there longer.
We have to use the moon to operationally understand how to live and work on a planet.
There are many ideas, but actually putting them into practice is the final step that's missing.
It'll be great to see humans return to the moon.
When this will happen is not yet clear, but science is making it possible to survive on the moon. On this Wednesday in 1969, the world was holding its breath. Mankind was witnessing a historic mission. On board Apollo 11, astronauts Neil Armstrong, Michael Collins, and Edwin Buzz Aldrin had a goal mankind had not yet reached: to fly to the moon. 5 days later, in the early morning of July 21st, Neil Armstrong uttered his unforgettable words.
It's one small step for man, one giant leap for mankind.
Armstrong and Aldrin spent a total of 2.5 hours on the surface of the moon. As they collected rock samples and raised the American flag, they were watched live by 600 million people. Only a few of them were aware that the successful moon landing was hanging by a thread. In NASA's Mission Control Center in Houston, Capcom Charlie Duke had direct radio contact with Neil Armstrong. Now 82 years old, he can still recall the dramatic moments.
We get very, very tight on fuel. I call 60 seconds, which meant he had 60 seconds to land, and I called 30 seconds. The tension is rising in mission control. You could hear a pin drop, and we were holding our breath. Will we make it? I called 30 seconds, and then 13 seconds later he landed. But it was very, very tight and very close to an abort.
Yet the first lunar landing was a success. 3 years later, Charlie Duke got his own entry in the annals of space travel.
John Young and I were the fifth landing on the moon back in April 1972, and I was the 10th man to step onto the moon. Once we landed, I just erupted with enthusiasm. I shouted into my, we had our helmets on and fully suited up, and I just shouted in my helmet, Houston, old Orion is finally here, Houston. Fantastic.
On the surface of the moon, Charlie and his commander, John Young, carried out experiments, for example, on radiation protection and heat flow.
It was awesome. It was beautiful, one of the most beautiful deserts I'd ever seen. Gray, very rough topography, up and down, hilly craters, rocks, hills, everywhere. And Our objective was to explore this valley, so I was excited. I was very happy to be there. You were almost overcome with the thought of, I'm on the moon, and I'm on the moon.
That's it. We're going home again, jiggity jig. Wow.
On April 24th, 1972, they lifted off again.
What a ride.
Only one further Apollo mission followed half a year later.
I'm very disappointed that we haven't had somebody go back. I thought that NASA would be extremely optimistic about going back to the moon. We need to build a station on the moon, similar to Antarctica, where we have a science station on Antarctica. And that's a very hostile climate in Antarctica, but we do it. And I think we could do the same thing on the moon.
Antarctica is the Earth's most extreme continent. Nowhere else is it this cold, with temperatures of minus 90 degrees Celsius being measured here. "98% of the mainland is covered by ice. That's 3/4 of the Earth's freshwater reserves. The surface is 1.5 times the size of Europe and twice as large during the Antarctic winter. Only a few animals can survive here. Several types of penguin, such as the emperor penguin, have adapted to the hostile environment, as have a few types of seals. The conditions here in the eternal ice resemble the barrenness of the moon most closely. Which is why a team of researchers from Bremen have made the long journey to the far south. The 14 members of the German Aerospace Center, DLR, will spend 2 months at the research station Neumeier 3.
We're growing between 15 and 20 different species of plant. As a highlight, we also have little strawberry plants. We hope we can get them to flower so we can harvest strawberries in a few months.
Until the mobile greenhouse reaches the Antarctic by ship, the team has to take good care of the delicate strawberry plants. Inside the station, Daniel Schubert and Konrad Zeidler have tried to create the most ideal conditions.
Strawberries are difficult to cultivate, and that's why we've improvised and built our own little makeshift greenhouse. Of course, it's not optimal, but we don't have much of an alternative if we want to keep the strawberry plants alive.
It will take at least a few more days for the greenhouse to arrive. Then the experiment here can really get going. And soon, on the moon? In order to live and work on the moon for a longer period of time, worldwide research has to consider the conditions there and the differences to planet Earth. "71% of the Earth is covered in water. It has an atmosphere, a layer of air and gases that surround it and protect it, for example, from meteorite impact and damage from various types of radiation. It also ensures that temperature swings are moderate. 400,000 kilometers away, things look rather different on the moon. Water would have to be extracted from lunar sand by evaporating and condensing it. The moon has no atmosphere to protect it from the impact of any flying objects. It is also exposed to dangerous cosmic radiation. Temperatures rise and fall so dramatically that humans could not easily survive. To make that possible in the future, international students of the European Space Agency are conducting research with various experiments at the European Training Center for Astronauts in Cologne. Dr. Aidan Cowley is in charge of the spaceship EAC project. Outside the center, a lunar station will be built for test and research purposes.
So what you're looking at is a foundation at the moment, but in the next few months this is going to rapidly change into a building. We're going to have a large 34-meter diameter dome. We're going to have 700 tons of regolith simulant. Regolith is the name of the material you find on the lunar surface.
A small settlement, for now in Cologne, but in the not-too-distant future, one on the moon too. This is how the scientists imagine it will look. Inside, there's an airlock and a technical area. The main room is provided with daylight. Like in the ISS, the oxygen supply is provided by chemically based air preparation.
Another good example of why we should go back to the moon would be to understand the radiation environment. So if you're in low Earth orbit at the moment, you have the magnetosphere of Earth protecting you to a certain degree. But the minute you move beyond this, you go to the lunar environment, you no longer have that protection. And now you've got an entirely new radiation environment that will have a different effect on humans.
The lunar habitat will protect humans from this radiation with a strong outer layer.
This is the protective layer that we want to build. So the idea is that we take the material that is already on the moon, and by applying the microwaves, we could put it around the lunar habitat and build like a solid structure that will protect the lunar habitat from the meteoroids, the radiations, and so on.
Student Oriane Garcia from France is producing the heat required to sinter the powdery regolith, baking it into a hard layer. At the moment, however, it looks more like pebbles than a flat surface. On the moon, special robot vehicles would spread the lunar sand and sinter it at the same time, which would take about 3 months. Back then, the Apollo astronauts didn't have such a protective building.
Well, in 3 days, it wasn't bad. You could survive with just the regular protection that we had.
It took about 40 years for the scientists to figure out what the Apollo missions really brought back. It takes that long. You have to develop the instruments to be sensitive enough to learn what these stones, 300 kilos, almost 400 kilos of stones that have been brought back from the moon, what they really tell us.
As you come around there, there's a rock in the near field on this rim that has some white on the top of it. We'd like you to pick it up as a grab sample.
The 12 Apollo astronauts were not allowed to keep any souvenirs. The original lunar regolith was simply too valuable. Just a stone's throw away from the research center in Cologne is the DLR's Institute for Solar Research. Here, too, scientists are researching regolith radiation protection. Professor Matthias Spall and his team seek the most moon-like conditions possible.
What's available in abundance on the moon is moon dust and plenty of radiation from the sun. We would need several meters of moon rock or moon dust as protection from radiation from the sun and other cosmic sources. And that's one of the things that we're researching.
The experiment is called Regolith, a word coined to combine regolith and light. Of course, it doesn't use real lunar regolith, but a simulant which has similar properties, and will be sintered to an entire brick using layered 3D printing.
What we want to show is that we can really produce a 3D object, whether X, Y, or Z, in a vacuum. And this is the technology we're developing here.
There's a vacuum on the surface of the moon. To simulate this, Miranda Fateri and Alexandre Meurice from France are creating the experiment in a vacuum chamber.
Our objective is to see what the mechanical properties are if we sinter something in a vacuum. If something better comes out, can we construct a better building with it or not?
The strong xenon beams imitate the sun and can create a constant heat of around 1,100 degrees Celsius. Channeled into one ray, they hit the 3 levels of moving moon sand below. It can take up to 5 hours under lunar conditions to bake a three-dimensional object such as a brick.
We want to see whether anything comes out under the vacuum, and then do the chemical analysis. But the chamber is too small and very hot. When we have a bigger chamber, we can build a better cooling system and bigger components.
Scientists have to find the right parameters so that in future, today's result will look like the brick sintered without a vacuum. As a last step, they have to replace the artificial light with their solar furnace, which consists of 159 square mirrors and concentrates the light energy. It produces the necessary heat through constant sun radiation as exists on the moon.
You have to make use of every resource you have. And so I think 3D printing structures for habitations, all these things that we can do now with the existing infrastructure, or existing materials on the surface will be something we'll want to take advantage of.
Back to the Antarctic. The conditions can change unpredictably. With the possibility of wind speeds of up to 60 knots, that's hurricane force. The weather here is the deciding factor. It's exactly the right testing ground for the scientists with the perfect conditions for their research.
The Antarctic is the most remote continent of the world. It's not easy to reach. The people living here are dependent on the technology which keeps them alive, just like in a space mission. So it's the best place to test the whole operation of the greenhouse.
Almost everything is prepared for their Project Eden ISS, where they're planning to grow vegetables and strawberries in a mobile greenhouse. This platform has been standing here for a while, 400 meters away from the German research station Neumayer 3. The mobile greenhouse should have arrived here days ago, but the cargo boat transporting it to the site is making slow headway through the thick pack ice. 14,000 kilometers away in Germany, moon research is also being carried out. Various experiments for the project spaceship EAC are being carried out at the European Astronaut Training Center in Cologne. Belgian student Sander Koene is working on a virtual environment where future visitors to the moon can train.
With a simulation like this, we can train them in the virtual reality as if they were already on the lunar base, and then have them interact with a digital rack and completely be able to do the experiment beforehand, instead of just being in a training room with a rack in front of you.
The virtual moonscape is still in the development phase. At some point, however, it could help with the preparation of future missions. A few rooms away, colleague Michael Regolith is busy working with different devices. His specialist area is 3D printing.
This is a 3D printer. It works with polymer, and the polymer is stick behind, and basically it warms it up in here, and then it melts. And when it melts, you can put it over a surface. It gets cold, so it gets stick to the bed. And you can print lane by lane and then layer by layer and make a 3D object.
Heating, melting, printing. But for the next step, Michele is particularly interested in the reusability of the plastic.
What we are doing is here check if the materials work properly in the moon. And afterwards, basically, we will check with our piece if we crash it, and then we re-extrude it with this machine again and print it again if it works the same as the object before.
The coil containing the plastic would of course have to be much larger when it is transported to the moon. But once it's there, the plastic could always be reused. In Bordeaux, France, the 3D printing process is being researched in a parabolic flight. Professor Jens Günster from BAM in Berlin, the German Federal Materials Testing Institute, has developed equipment with his team to enable parts such as tools to be made from metal powder in zero gravity.
The aim of the experiment is to try out a new process of sucking in powder and then trying to fix it in a zero-gravity environment. So in principle, you can produce parts on demand. The part which has been sintered with the laser onto this plate should be able to be taken out and is ready for use.
Before each flight, the scientists draw their conclusions from the previous flight, making minor adjustments to try and improve the results of their experiment.
This is our third flight day. Last time we switched the material, and this time we have adjusted the parameters of the equipment to be able to apply the layer of powder. I'd say we managed to get about 70% of the powder onto the layer, and the rest flies away. We need to improve that. We can't have the powder flying around.
The Berlin research team is just one of many. In total, the participants here in Bordeaux fly for 4 hours on each of 3 days. There are 31 parabolas per flight. The aircraft rises steeply upwards from its horizontal position, reduces the thrust of the turbines, and flies for around 22 seconds at zero gravity. That is a particular challenge for the scientists, as the gravitational force during a parabolic flight varies. They've adapted the structure of their experiment accordingly. The experimental apparatus looks like this. The metal powder is in a container at the beginning of the parabolic flight. From there, it's spread in a layer over the base plate. So that it doesn't fly away in zero gravity, it's sucked in by gas from below and kept on the base plate, also during zero gravity. Then a laser melts the relevant information onto the freshly applied powder. It melts the loose metal powder into a compact structure. This is done with every layer, producing a three-dimensional object, in this case a spanner. Günster and his team can follow this process, which is repeated several times via the installed webcams. The final results can be seen a little later in the laboratory. The metal powder has really been transformed into 2 small spanners. The experiment by Günster's research group was a success. In the not-too-distant future, all tools could be produced this way in space. In the Antarctic, the long wait is over. The cargo ship, the Regolith 2 from South Africa, has managed to break through the ice and the unloading can finally take place. After a 10-day delay, the German scientists watch their mobile greenhouse being unloaded from the ship. Unloading on the ice has its hazards. Although the area around the ship is frozen, the layer of ice is thinner than further inland. The whole process takes around 90 minutes. In the end, all is well, and the squad sets off back to base. It's 23 kilometers away from the unloading point to Neumeier 3. Although there is no darkness in the Antarctic summer, as the sun never goes down, they still have a regulated 8-hour working day. This day ends with the long-awaited arrival of the container at the station. The next day begins early. It's time to build the greenhouse. The scientists have a whole freight container full of equipment which they have to unpack and inspect after such a long journey. At the same time, the mobile greenhouse is assembled. It's made up of 2 6-meter-long containers and is precision lifted by crane onto the platform. Once this task has been completed, the Eden ISS project can really get going. Looking inside the container, we can see how the Antarctic greenhouse works in detail. The first part contains the services sector, where all the technical systems, such as air and heat management, are monitored and controlled. The second part contains herbs, vegetables, and lettuces, which can all self-pollinate with the help of ventilation. The technology which allows them to grow is called aeroponic. Instead of transporting heavy soil into space, the roots of the plant are sprayed with a water nutrient solution. LED lamps containing the right color composition are then mounted above to imitate sunlight. Complex water and air cleaning systems complete an independent and sustainable ecosystem.
People think that the plants are only for us to eat, but there are other reasons we take the plants with us. They provide us with oxygen to breathe. They need the carbon dioxide that we humans breathe out. It's a perfect symbiosis.
4 days after the arrival of the container, everything is installed to start up operations. Almost 2 weeks later than planned, the German scientists can finally start sowing the seeds. Of course, the long-nurtured strawberry plant has top priority. As carefully as if they were performing surgery, Schubert and Seidler take care of the sensitive plant. After bathing it in water, the strawberry plant is put into its new home using mineral wool and a plastic holder. The researchers are optimistic that most of the plants will thrive. But they're a bit concerned about the diva of their crops, the strawberry plant.
If you go on long-term missions, such as the one to the moon, you can use strawberries as an incentive food, just to keep the isolated team in good mental shape. If this experiment works here in the Antarctic, we're pretty confident that the whole thing will work on the moon, too.
But on the moon, the conditions are more difficult and unpredictable. Although the container could stand without being further secured due to the moon's reduced gravity, the parts of the autonomous system still have to be transported there. Yet there's one key component missing on the moon, which is guaranteed here by the connection to the Neumayer 3 station: electricity. In Edinburgh, Scotland, a team is working on a solution to this problem. At the Harriet Watt University, Jürgen Schleppi is researching the topic of solar energy.
Of course, on the moon, we can't just plug our devices into sockets. We have to consider what kind of resources are available for producing energy. There are no rivers, there's no wind on the moon, there's no atmosphere. What is available is sunlight, and it's better than on Earth because it is not weakened by the atmosphere.
Jürgen Schleppi wants to produce mirrors to create energy. His experiment is also about how to use lunar regolith.
We'll have the materials we've brought with us, and there's this basaltic sand. What we can build out of basaltic sand is relatively simple bricks or walls by heating the material or baking. We can go one step further and produce basaltic glass from the material.
Schleppi uses an ordinary microwave oven to make glass from the moon sand simulant. He grinds the molten regolith, which is turned into glass, as smoothly as possible. The glass brick still needs a reflective surface. This is made in the final and most complicated part of the mirror production process. On the moon, there is an endless vacuum, but here it has to be created artificially. Schleppi fixes the glass elements which have been produced in recent weeks onto the frame of the vacuum chamber. Before he seals it, he adds one small piece of aluminum, which is heated and then evaporates, distributing millions of tiny particles.
The glass is different, but the aluminum is the same type we use for normal mirrors. It's looking pretty good now. It's not transparent anymore. So we can slowly turn off the system.
The aluminum, which was heated in the vacuum, is not only supposed to coat the inside of the vacuum chamber's glass dome, it is primarily meant to coat the experimental glass stones.
It looks really good. The mirrors have turned out really well. They should be able to reflect our artificial sunlight well.
That's what matters at the end of his experiment. It will only be a success if the mirrors made of moon sand can also harness energy from light. To test it, the researcher has built his own construction. His homemade mirrors have to pass the comparison test.
So here we have a reference surface, which reflects sunlight, or rather the artificial light we're going to produce from this surface to the lens, which is attached to a solar cell. The lens concentrates the light onto the solar cell, and then we can produce electricity, which we can measure at a certain voltage. We can read it here on the meter. With the reference surface mirror, we expect to produce about 2 volts. Lights out. 2.46 volts. That looks good. It's working.
2.46 volts are produced with an ordinary mirror surface. This is a reference level for the mirror made of the imitation lunar sand.
We're going to find out now whether it'll work in the way we imagine. 2.23 volts. That's great. We're only losing about 10% compared to the reference mirror surface. That's really good for the first attempt. Very successful.
So the German scientist has really succeeded in producing energy from lunar regolith and light.
You know, if we can mine those resources and turn them into mirrors or some other solar type of energy, that's definitely going to be a way we're going to maintain a base or a presence on the moon. But the biggest challenge, I think, for living on the surface of the moon is dealing with the power needs, dealing with the infrastructure to maintain systems, especially during the lunar night. What's interesting about the moon is almost anywhere on the surface, you're going to experience 14 continuous Earth days of light, followed by 14 continuous Earth days of night.
This day and night rhythm of the moon can be illustrated with the help of a solar cell, which would be positioned on the side of the moon that we always see from Earth. This phenomenon arises due to so-called synchronous rotation. The moon needs exactly the same time to orbit the Earth as it does to rotate on its own axis, almost 28 days. Since it rotates on its own axis, this means that the side with the solar cell faces the sun for 14 days. During this period, the energy production by the solar cell is constantly stable. For the other 2 weeks, the solar cell is on the shadow side. Solar energy cannot be produced during the long lunar night.
And that night, it's cold, dark, there's no solar energy to draw from. You have to have power that can keep alive during those 14 days.
So we need small, efficient batteries. We need very efficient solar cells. If we can develop batteries that'll last 2 weeks for lunar night and do all of the things you want to do up on the moon during that time, then that's the answer.
For Duke's 3-day trip to the moon and the other equally short Apollo missions, energy was not a problem. A much greater challenge back then was moving around in the bulky spacesuits. The astronauts only learned to handle it once they reached the moon.
There are three ways to move around on the moon. I generally did a walk, just a regular walk, stiff-legged walk that you could really get going fast. But if I was going uphill, I would kangaroo hop uphill.
I like to skip along, or whatever you call it. I can't get my left leg in front of me.
Downhill, it seemed to be better skip, one leg in front of the other, and you skip down like this. So it depended, to me it depended on the terrain that I was on, which one I used. I think we really need a better spacesuit to stay on the moon a long time.
It's precisely this project, the development of a spacesuit for the Moon and Mars, which is being pursued at the Massachusetts Institute of Technology in Boston. Professor Dava Newman is trying to adapt the old spacesuit to the conditions on the Moon.
Because right now the current spacesuit is 140 kilos. It's for space station. It was for shuttle, so that's okay in weightlessness. But when we get to the Moon and Mars, we're in a gravity environment.
The Moon only has about 17% of the Earth's gravity, allowing large leaps, but these can backfire, especially in heavy spacesuits.
Come on out here and give me a salute. Big Navy salute. Off the ground, on the floor.
How do I make someone much more like an Olympic athlete? How do we perform and not waste my energy working against a suit, but put all that energy into performing? So you really have to think about a completely different design. The only other way to keep someone alive and put pressure on them is to basically put it right onto the skin. So that's called mechanical counterpressure.
Dava's version of the suit is skin tight, exerting pressure on the body and the right pressure within the body. This means that human tissue is not stretched and blood doesn't clot. It's made of 3 layers. The inner layer controls body temperature, the middle layer provides stability and flexibility, and the outer layer is protective. If the suit tears, it can be easily repaired. The outdoor work on the Moon can then continue. With current spacesuits, a leak could be lethal, as the gas it contains to maintain the pressure necessary for human survival could leak out. This is what makes it so heavy and hinders the astronauts' movement, a major disadvantage compared to MIT's version.
We've been working on it for a while, for the last 15 years, and so far it seems feasible.
Their moon suit is indeed feasible, but whether it will be deployed remains to be seen. Elsewhere, the successful implementation of an experiment is more concrete. In the German Aerospace Center in Bremen, the scientists of the Eden ISS project have been back from the Antarctic for a month, minus the one who has to stay and look after the plants in the greenhouse container. They ask how things are going.
Since the start of the isolation, it's actually been quite nice here. At last, there aren't so many people around. It's quite pleasant. The greenhouse is doing well. The plants are going great. We had a few teething problems at first, but on the whole, it's all going pretty well.
The Antarctic gardener regularly reports via video conference on the development of the plants.
The strawberries were really sensitive, and sadly they didn't make it. We had to stop the experiment early. We're making a new start with the experiment from scratch. Because we don't have seedlings in there anymore, we've planted them straight from seed, and we think it'll be a success.
Every day since their return, scientists have been observing the growth. Today is harvest day, and gardener Paul Zabel can finally reap the benefits of his weeks-long work.
You can see our first harvest here on the table. The lettuce plants have done really well. We've got plenty of those for the next few days. The cucumbers are doing pretty well too. Some of them are really big. They're going to be weighed now, and then I'll think we'll probably have some of them for dinner tonight.
Paul Zabel and the other 9 researchers at the Neumeier 3 station will have fresh vegetables to eat. Not only today, but during their whole isolation period in the Antarctic winter. The Eden ISS project is already a success, and the basis for a food supply for future trips to the Moon has been created.
In a perfect world, we could put a moon habitat, or at least a greenhouse on the moon within the next 15 to 20 years.
But this isn't a perfect world. The necessary research funding for speedy progress is not as easy to come by as it was in times of the Apollo missions.
We don't want to just do Apollo again. That's not what our goal is. Our goal is sustainable, long-term exploration.
50 years after the first moon landing, we will probably have to wait a few more years or even decades until the next one. But preliminary preparations are underway.